Hello dear students, we have learned that Bohr used various scientific developments in the field of physics and work of other scientists to propose his model of atom with well-defined values of energy and angular momentum of the electron moving in an orbit of radius r around the nucleus. But his inability to explain splitting of the line spectra of hydrogen further in electric and magnetic fields, that is Stark and Zeeman effect, led the scientists to think further. And to overcome the shortcomings of the Bohr's model, attempts were made to develop a more suitable model for atoms. Two important developments which contributed significantly in the formulation of such a model were dual behavior of matter and Heisenberg's uncertainty principle. Dear students, Bohr proposed his model of atom in 1913. French physicist de Broglie in 1924 proposed that matter, like radiation, should also exhibit dual behavior, that is, both particle and wave properties. This means that just as photon of light or energy has momentum as well as wavelength, electrons should also have momentum as well as wavelength. According to him, wavelength lambda and momentum p of a material particle are related as lambda is equal to h upon p, or we can elaborate it further as lambda is equal to h upon mv, where m is the mass of the particle and v is the velocity with which it is moving and p is the momentum. De Broglie prediction was confirmed experimentally when it was found electron beam undergoes diffraction, a phenomena characteristic of waves. This fact has been put to use in making an electron microscope. Electron microscope is based on the wave-like behavior of electrons. Just as an ordinary microscope utilizes the wave nature of light, an electron microscope is a powerful tool in modern scientific research because it achieves a magnification of about 15 million times. According to de Broglie, every object in motion has a wave character. The wavelength associated with ordinary objects are so short because of their large masses that their wave properties cannot be detected. The wavelengths associated with electrons and other subatomic particles with very small mass can, however, be detected experimentally. The solution I am sure you all can find very easily. You can see the proceedings on the screen too. The lambda can be found by substituting various values. Werner Heisenberg, a German physicist, was studying the developments in the scientific world. In 1927, he stated uncertainty principle as a consequence of dual behavior of matter and radiation. It states that it is impossible to determine simultaneously, that means at the same time, the exact position and exact momentum or velocity of a subatomic particle like electron. Mathematically, it can be given as an equation shown on the screen. Delta x into delta p is greater than or equal to h upon 4 pi. We can also change it as delta x multiplied by m delta v greater than or equal to h upon 4 pi, where delta x is the uncertainty in position and delta p or delta v is the uncertainty in momentum or velocity of the particle. Dear students, tell me, how are you able to see me? You are able to see any object when the light radiations fall on the object and they are reflected back to you. Analogously, in order to determine the position of an electron, you have to locate the electron. That means we must use a meter stick calibrated in units of smaller than the dimensions of electron. See, I am bigger than the wavelength of the light that is falling on me, isn't it? So, if some light has to get reflected from the electron, the wavelength of the light has to be smaller than electron, otherwise it will just pass over the electron, isn't it? So, keeping this in mind that an electron is considered as a point charge and is therefore dimensionless, so to observe an electron, we can illuminate it with light or electromagnetic radiation. The light used must have a wavelength smaller than the dimension of electron. The high momentum photons of such light, P is equal to h upon lambda, would change the energy of the electrons by collision, isn't it? If the wavelength is small, the energy is high. In this process, we no doubt would be able to calculate the position of the electron, but what we have done? We have changed the velocity of the electron after the collision. One of the important implications of the Heisenberg uncertainty principle is that it rules out existence of definite paths or trajectories of electron and other similar particles. The effect of Heisenberg uncertainty principle is significant only for motion of microscopic objects and is negligible for that of macroscopic objects. This can be seen from the examples as if uncertainty principle is applied to an object of mass say about a milligram, only if both the position and the velocity of the electron are known exactly at the same time. This is not possible according to the Heisenberg's uncertainty principle. Bohr model of the hydrogen atom therefore not only ignores dual behavior of matter but also contradicts Heisenberg's uncertainty principle. So now we have the task for the day. If the position of the electron is measured within an accuracy of plus minus 0.002 nanometers, you have to calculate the uncertainty in the momentum of the electron. Suppose the momentum of the electron is h upon 4 pi m multiplied by 0.05 nanometer. Is there any problem in defining this value? Let's have another question. A microscope using suitable photons is employed to locate an electron in an atom within a distance of 0.1 angstroms. What is the uncertainty involved in the measurement of its velocity? So, my dear students, in the wake of the failures of Bohr's model of an atom, a new model was required which could account for the wave-particle duality of matter and be consistent with Heisenberg's uncertainty principle. This came with the advent of quantum mechanics. Till now, we were dealing with classical mechanics based on Newton's law of motion, which successfully describe the motion of all macroscopic objects such as falling stone, orbiting planets, etc. These have essentially a particle-like behavior and ignore the concept of dual nature of matter, especially for subatomic particles and the uncertainty principle. The branch of the science that takes into account this dual behavior of matter is called quantum mechanics. When quantum mechanics is applied to macroscopic objects for which wave-like properties are insignificant, the results are the same as those for the classical mechanics. The Schrödinger wave equation is a partial differential equation. It uses the concept of energy conservation, that is kinetic energy plus potential energy is equal to total energy, to obtain information about the behavior of an electron bound to a nucleus. So, to to account for the dual nature of electron and to find its position around the nucleus, a partial differential equation in 3 dimensions was written. For a system such as an atom or a molecule whose energy does not change with time, the Schrödinger wave equation is quite complex and takes into account the total energy of the system. It takes, that is, the kinetic energies of all the subatomic particles, that is electrons, nuclei, attractive potential between the electrons and the nuclei, and repulsive potential among the electrons and nuclei individually. Simply, it is written as H psi is equal to E psi, where H is a mathematical operator called Hamiltonian. Solutions to this equation gives the values of E, that is the energy of electron, and psi, the wave function. The wave function is a mathematical function whose value depends upon the coordinates of the electron in the atom and does not carry any physical meaning. Dear students, I am sure in your mathematics class you must have solved quadratic equations for the values of variables, and in that you accept only those solutions which are real and ignore the imaginary values. Similarly, for Schrödinger wave equation, only those solutions of the equation were accepted which were single valued, continuous and finite. When Schrödinger equation is solved for hydrogen atom, the solution gives the possible energy levels the electron can occupy and the corresponding wave functions psi of the electron associated with each energy level. These quantized energy states and corresponding wave functions, which are characterized by a set of 3 quantum numbers, that is principal quantum number n, azimuthal quantum number L and magnetic quantum number ml, arise as a natural consequence in the solution of the Schrödinger equation. So, my dear students, the n, the L and the m, how are we getting them? These are coming as the solution to the Schrödinger equation, which are finite, single valued and continuous. When an electron is in any energy state, the wave function corresponding to that energy state contains all information about the electron. Such wave functions of hydrogen or hydrogen-like species, that is with one electron, are called atomic orbitals, and the one electron species are called one electron systems. The probability of finding an electron at a point within an atom is proportional to psi square, that is square of the wave function psi at a given point. The applications of Schrödinger equation to multi-electron atoms present a difficulty. The Schrödinger equation cannot be solved exactly for a multi-electron atom. This difficulty can be overcome by using approximate methods. The principal difference lies in the consequence of increased nuclear charge. Because of this, all the orbitals are somewhat contracted. Furthermore, for multi-electron systems, unlike the orbitals of hydrogen or hydrogen-like species whose energies depend only on the quantum number n, the energies of the orbitals now depend on quantum numbers n, that is the principal quantum number, and L, that is the azimuthal quantum number. We have learned till now that the solutions to the Schrödinger wave equation, which are finite, single valued and continuous, give us the quantum numbers. These quantum numbers define an orbital which give us the probability of finding an electron around the nucleus. A large number of orbitals are possible in an atom. Qualitatively, these orbitals can be distinguished by their size, shape and orientation. An orbital of smaller size means that it is more closer to the nucleus, and hence the chances of finding the electron near the nucleus are more. Similarly, shape and orientation mean that there is more probability of finding the electron along certain directions than along others. Atomic orbitals precisely distinguished by what are known as the quantum numbers. Each orbital is designated by 3 quantum numbers as n, l and ml. The principal quantum number n is a positive integer with values as n is equal to 1, 2, 3 and so on till infinite. The principal quantum number determines the size and to large extent the energy of the orbital. For hydrogen atom and hydrogen-like species like helium plus, lithium 2 plus, etc., energy and size of the orbital depends only on n. The principal quantum number also identifies the shell. With the increase in the value of n, the number of allowed orbitals increases and are given by n square. So, inside the shell there are orbitals and the number of orbitals is given by n square. All the orbitals of a given value of n constitute a single shell and are represented by the letters n is equal to 1, 2, 3, 4 or K, L, M, N. I am sure you can relate it to the Bohr's orbits, which were also given the name KLMN, but the Bohr orbits were circular, they were 2-dimensional. Now, when we are talking of the quantum mechanical model, we are talking of a shell where it is 3-dimensional. So, the size of an orbital increases with the increase of principal quantum number n. In other words, the electron will be located away from the nucleus. Since energy is required in shifting away negatively charged electron from the positively charged nucleus, the energy of the orbital will increase with the increase of n. The next quantum number, that is the azimuthal quantum number L, is also known as the orbital angular momentum or subsidiary quantum number. It defines the 3-dimensional shape of the orbital. For a given value of n, L can have n values ranging from 0 to n minus 1. That is, for a given value of n, the possible values of L can be 0 to n minus 1. For example, when n is equal to 1, what are the values of L? Because we said L can take a value of 0 to n minus 1, so it is 0 only. But when we come to n is equal to 2, the possible values of L can be 0 and then n minus 1, that is 1. So, with n is equal to 2, L will have 2 values, 0 and 1. Can you tell me what will be the values of L with n is equal to 3? I am sure you have guessed. For n is equal to 3, L will have 3 values, and what are those? They will be 0, 1 and 2. Each shell consists of 1 or more subshells or sublevels. My dear students, like for n we gave the names K, L, M, N, similarly the subshells are also named. So, if the value of L is 0, the name of the subshell is S. If it is 1, it would be P, for 2 it is D, for 3 it is F and so on. The permissible values of L for a given principal quantum number and the corresponding subshell notations can be seen on the screen. For n is equal to 1 and L is equal to 0, the subshell notation is 1s. For n is equal to 2 and L is equal to 0, it will be 2s. For n is equal to 3 and L is equal to 0, it would be 3s. Similarly, you can go on, as you can see on the screen. If n is equal to 4 and L is equal to 3, then the name would be 4f. So, dear students, we have learnt about the 2 quantum numbers n and L. Now, it is turn for the third one, that is the magnetic orbital quantum number ml. This quantum number gives us information about the spatial orientation of the orbital with respect to the standard set of coordinate axes. Thus, the values for the magnetic quantum number ml for a given value of L can be starting from minus L to 0 and from 0 to plus L. Thus, for L is equal to 0, the only permitted value of ml, the magnetic quantum number, is 0. And for L is equal to 1, the orbital quantum number would be minus 1, 0 and plus 1. Now, if I may ask you, for L is equal to 2, what would be the values of ml? I am sure you can tell me. The values of ml would be from minus 2 to 0 and from 0 to plus 2. That is, the values would be minus 2, minus 1, 0, plus 1 and plus 2. That means 5 values of d orbitals. So, the relation between the subshell and the number of orbitals associated with it can be seen on the screen. Here you can see for a value of L as 0, 1, 2, 3, 4 or 5, the name of the subshell would be S, P, D, F, G or H respectively. And for this, the number of orbitals respectively would be 1, 3, 5, 7, 9 and 11. The three quantum numbers labeling an atomic orbital can be used equally well to define its energy, shape and orientation. But all these quantum numbers were not enough to explain the spectral lines observed in the case of multi-electron systems. That is, some of the lines actually occur as doublets, that is 2 lines closely spaced, or triplets, that is 3 lines closely spaced. This suggests the presence of a few more energy levels than predicted by the 3 quantum numbers n, L and ml. In 1925, George Uhlenbeck and Samuel Goudsmit proposed the presence of the 4th quantum number known as the electron spin quantum number ms. My dear students, one thing to remember here is the first 3 quantum numbers n, L and ml are the result of the solutions to Schrodinger wave equation. But this new quantum number, that is the spin quantum number, was introduced later. It does not originate from the Schrodinger wave equation. An electron spin around its own axis much in a similar way as Earth spins around its own axis while revolving around the Sun. In other words, an electron has, besides charge and mass, an intrinsic spin angular momentum. The spin angular momentum of the electron is a vector quantity. It can have 2 orientations relative to the chosen axis. These 2 orientations are distinguished by the spin quantum numbers ms, which can take 2 values, plus half or minus half. That is, whether the electron is spinning anti-clockwise or clockwise. These are called the 2 spin states of the electron and are normally represented by 2 arrows, spin up and spin down. The 2 electrons that have different ms values, one plus half and the other minus half, are said to have opposite spins. An orbital cannot hold more than 2 electrons, and these 2 electrons should have opposite spins. So, my dear students, we have come to a very interesting part of this chapter. We have got the 4 quantum numbers n, L, ml and ms, which give us the address of an electron. It is something like, if I wish to find a boy Atul. Suppose I wish to find a boy by the name Atul, and I know that he studies in a school ABC Senior Secondary School. So, first of all, I will go to the school ABC Senior Secondary and ask for him. So, if I have to find a particular electron, I will go to the atom, let us say hydrogen atom. Inside the hydrogen atom, I have to know which shell does the electron belong to. Similarly, I can say that Atul studies in class, let us say 11A. So, class 11A becomes the shell. Inside the shell, there are rows. Inside the class, there are rows. So, inside the shell, there are subshells like rows. So, I say Atul sits in the first row. But where in the first row? Inside the subshell, there are orbitals. So, we say Atul sits on first row, first seat, that is the orbital is the first seat. But on the seat, two students can sit, one on the right hand side, another on the left hand side. Two students cannot sit at the same point, isn't it? Similarly, inside the orbital, the electron can have two different spins. That means each orbital can hold only two electrons, as on one seat, two students can sit, either on right or on left. So, if I have said on the right hand side, the boy sitting is Atul, the address of Atul is found. So, we can quickly say that the boy who sits on the right hand side on the first seat in the first row in class 11th A and belongs to the school ABC Senior Secondary School is Atul. So, that is the complete address. Similarly, you can say for the electron. I am sure you have enjoyed this analogy of finding the address of an electron and the boy named Atul. Now, it is time to do some problems. So, here comes the task for you. So, the task coming for you is an electron is in one of the 3D orbitals. Give the possible values of N, L and Ml for this electron. I am sure you can do this. The next question for you, using S, P, D, F notations, describe the orbital with the following quantum numbers: N is equal to 1, L is equal to 0. Next, N is equal to 3 and L is equal to 1. So, my dear students, I am sure now you will be able to explain the address of an electron using the principal quantum number, azimuthal quantum number, magnetic quantum number and the spin quantum number. You will also be able to calculate the number of orbitals associated with a principal quantum number. You will be able to use scientific conventions and symbols as per international standards. Learning has no boundaries. Now, with this as the base, why don't you explore more? Pick up some more books from your school library and solve some more problems based on the concept, because practice makes a man perfect. Happy learning. Thank you.